The tip of the thermometer sinks into the crimson sand. 48 degrees. No wind, no shade. Even sound seems to have melted away. 5 minutes. Then the human body stops sweating. The kind of ground experts call deadly. Cracked. Crimson. Endless to the horizon. But 10 meters below, beneath that very same ground, another number begins to glow. 22 degrees. And in the darkness, a violet-pink light pulses at steady intervals, as if it's breathing. Down there, directly beneath death itself, something is growing. Silently. Untouched by human hands. No power lines, and no one has seen it. Until now. You're probably watching this video with a glass of water in front of you. Maybe a tomato, or a handful of fresh greens. It all looks ordinary, doesn't it? But almost no one thinks about the journey that vegetable took before it reached your plate. A refrigerated truck, then another, then a warehouse, then yet another truck. Thousands of kilometers, a supply chain stretching across days. With every transfer, it loses a little more freshness, consumes a little more energy, and sends a little more food to waste. The reason is simple. Most of the planet's land surface is made up of deserts or semi-arid regions. On agricultural maps, these lands are almost always left blank. The sun is considered too unforgiving, the water too scarce, and the soil too barren. As a result, most of the world's food is grown in a limited number of fertile regions, then transported across the rest of the globe. That transportation means energy. It means time. It means cost. And as the climate changes, those fertile regions continue to shrink, while the pressure on them grows year after year. And that's where the real problem begins. Because at the very same time, one of the most inhospitable landscapes on Earth undergoes a completely different transformation just a few meters beneath the surface. During the day, deserts behave like ovens. At night, like freezers. But that's only true for the first few meters. Just below that, the ground becomes a layer that feels as though it has forgotten the seasons the moment you place your hand inside it. Neither scorching hot, nor bitterly cold, but almost always the same. Summer or winter, day or night. It doesn't matter. Down there, the Earth keeps its own steady rhythm. This isn't actually a new discovery. We already know why wine cellars have been built underground for centuries. We know why root vegetables have long been buried in the soil to preserve them through winter. We know why ancient settlements sought shelter in hillsides and caves. Humanity learned this truth long ago. It has been using it for centuries. We simply never tried placing a farm beside it. I'd say the claim begins here. Beneath the world's driest, most barren lands, it may be possible to build a fully functional greenhouse capable of producing food. Without relying on sunlight, without rain, without even fertile soil. I know that sounds strange. When we picture a greenhouse, we all imagine the same thing. A glass roof, sunlight pouring through it, the warmth of the sun overhead. For nearly a century, we've associated agriculture with the same three ingredients: sunlight, rain, and fertile soil. If even one of them was missing, we assumed farming simply wasn't possible. But everything changes once you realize those three elements don't actually depend on one another. What a plant truly needs isn't sunlight, it's light at the right wavelengths. Like a key fitting into a lock, only a small fraction of the millions of colors in sunlight actually drives plant growth. The rest is simply heat, and sometimes even stress. What roots truly need isn't fertile soil. They need something to anchor themselves to. A plant doesn't require soil. It requires a surface that can support its roots. A thin sponge, a mesh. Under the right conditions, either can do the job. The weight of soil, the effort of transporting it, even the fact that it eventually becomes depleted. None of those have to be problems anymore. And what water truly needs isn't abundance, it's a cycle. The same drop, used over and over again, without ever being lost. Imagine using a single glass of water 100 times. Losses fall almost to zero. Evaporation stops being the enemy and becomes a resource. Once you solve these three elements separately, you begin to question why the very word greenhouse has always been tied to the surface, to sunlight, and to the open sky. Maybe the word itself has trained us to look in the wrong direction, just as the word home makes us picture four walls and a roof, even though a home can exist underground. So how do these three pieces come together? What kind of engineering makes this possible? That's where things become truly fascinating. But first, we need to see just how close this idea already is to your everyday life. The system is actually built on 3 layers, and the surprising part is that every one of them is based on technologies that have already existed and been used for years. The only new idea is thinking to bring them together inside the same excavation. The first layer is the ground itself. 10 meters below the surface, if you place your hand against the earth, it feels the same gentle, steady warmth, whether it's 48 degrees outside or the temperature has dropped to 5 degrees overnight. Think of it as a radiator, but one that works in reverse and burns no fuel. This is known as the thermal mass effect, and civil engineers have understood it for decades. Underground homes, tunnels, and even entire underground towns stay cool because of this principle. The only difference here is that the same principle is being applied not to a house, but to a farm. The second layer is light. Instead of relying on the sun, the system uses LEDs precisely tuned to the wavelengths plants actually need for photosynthesis. That isn't new either. Vertical farms have been growing vegetables for years inside warehouses in the middle of cities, places where sunlight never reaches. But here's the real twist. Those LEDs are powered by the abundant sunlight pouring onto the desert directly above. The very thing you're escaping becomes the source of your energy. And the solar panels don't have to sit directly above the greenhouse. They can be spread across vast stretches of otherwise unused desert, allowing energy production and food production to share the same landscape without competing for space. The third layer is water. Hydroponic systems, which feed plants through nutrient-rich water instead of soil, recover almost all of the water that would normally be lost in open field farming. In conventional agriculture, water disappears into the sun, the wind, and the sand. Inside a closed system, it remains in circulation like water, trapped in a sponge. The same drop is used again and again, with almost no loss. Even the moisture released by the plants isn't wasted. It's condensed from the air and returned to the system. None of these 3 layers is extraordinary on its own. What's extraordinary is that no one thought to bring all 3 together inside the same underground space. So what does that mean for everyday life? The impact can be felt in 2 different ways. The first is food production. Millions of square kilometers of land that are currently considered impossible to cultivate could, at least in theory, become productive farmland. In regions struggling with water scarcity, that could mean the vegetables on supermarket shelves no longer travel 3,000 kilometers to reach you, but just a few. Fresher food, lower costs, less waste. The days between harvesting a box of strawberries and eating them could shrink to just a matter of hours. The second is energy and infrastructure. The solar panels on the surface power the greenhouse while feeding any excess electricity back into the grid. In other words, the project generates its own energy from its own roof, or in this case, its own ceiling. No external power lines, no diesel generators, a self-sustaining system. And that opens an entirely new possibility for remote regions where electrical infrastructure has never reached. Technically, everything is ready. But being ready is not the same as being built. An agricultural engineer walks quietly between the rows, a small moisture meter in hand. Above, violet-pink LED lights cast a strange yet vibrant glow across the leaves, pulsing with the same steady rhythm, as if the entire place is breathing. The engineer stops and gently touches a leaf. Cool, moist, fresh. 10 meters overhead, the desert is still scorching beneath the relentless sun. But down here, there isn't the slightest trace of that heat. So if all three technologies already exist, why isn't there a large-scale underground greenhouse beneath a desert anywhere in the world? The answer isn't hidden in engineering. It's hidden in a single word. When we hear the word greenhouse, our minds automatically picture a glass roof with sunlight pouring in from above. When we hear underground, we think of shelters, mines, or storage facilities, but never agriculture. Those two ideas have never belonged in the same sentence because they never needed to. No one has ever looked into an excavation and said, "That's my farm of the future," until water and fertile soil became limits. And as those limits grow more serious, a question that was long ignored begins to resurface. What if the obstacle was never technical? What if it was simply hiding in a place no one ever thought to look? But the fact that it isn't a technical problem doesn't mean it will be built. Of course, as clean and elegant as this idea may look on paper, it faces two real obstacles. Both are serious, but neither is the dead end it first appears to be. The first is energy. Even if LEDs replace sunlight, they still require electricity, continuously, without interruption. In desert conditions, a power outage could destroy weeks of crop growth in a single night. But the solution lies in the very source of the problem. The same desert above the greenhouse has some of the highest solar energy potential on Earth. With enough solar panels and energy storage, the entire power demand can be met on site, without a single external power line. That doesn't mean we should underestimate the engineering hidden behind the words, "enough solar panels." But battery costs have fallen so rapidly over the past decade that this is no longer a theoretical solution. It's a solution that already exists today. The second obstacle is the initial investment. Excavating 10 meters underground, ensuring waterproofing, installing ventilation, and maintaining precise humidity control. All of it makes the project more expensive than a conventional greenhouse at the beginning. That doesn't make it impossible. It simply means the cost curve hasn't been scaled yet. A modular design, building multiple interconnected cells instead of one massive underground excavation, reduces construction risk while spreading costs over time. Instead of one enormous upfront investment, each new module is built faster and more affordably, using the experience gained from the previous one. As the system expands, it gradually makes itself cheaper. We've already seen this pattern in other industries. Just a decade ago, container-based vertical farms were widely dismissed as something that would never be economically viable. Today, many of them operate commercially in cities around the world, simply because costs fell as the technology scaled. The path toward underground greenhouses will most likely follow a similar curve. Both obstacles are real, but both end with the same word. Yet, so far, we've been looking at the skeleton of the system. Now it's time to go deeper, quite literally. The engineering layer. A depth of 10 meters isn't an arbitrary number. Dig too close to the surface, and daily temperature swings still reach the structure. Dig too deep, and the geothermal gradient begins to take over, causing temperatures to rise again. Around 10 meters, in most desert climates, those two effects balance each other out. It's the calm zone, as if the Earth itself has its own point of equilibrium. The structure isn't one enormous underground chamber either. It's designed as a network of interconnected cells, arranged like a honeycomb and linked by corridors. If one cell develops a problem, a leak or a mechanical failure, the others continue operating unaffected. Much like the watertight compartments of a ship, even if one floods, the vessel stays afloat. The ventilation system follows the same philosophy. Air circulates between the cells to regulate humidity, while allowing any single module to be isolated if necessary. If a disease or pest appears, it can be contained before it spreads. But that level of resilience doesn't come for free. And that's exactly where economics enters the picture. The economic layer. Desert land is often considered almost worthless, which is precisely why it's inexpensive. In traditional agriculture, one of the largest expenses is the land itself. Here, that cost drops to almost nothing. In some regions, the price difference between a hectare of fertile farmland and a hectare of desert can be as much as tenfold. Yes, excavation is expensive at the beginning, but when you combine nearly free land, on-site energy generation, and water recycling, the long-term equation begins to reverse. A high upfront investment is gradually offset by low operating costs within just a few years. The water bills and transportation costs that must be paid year after year in conventional agriculture become part of a single upfront investment in this system. So what could this actually mean for you? If you live in a region facing water scarcity, it could mean lower prices for imported vegetables. If you're a farmer, it could mean that land once considered unusable becomes valuable again. Behind all these numbers lies something much more tangible: everyday life. The environmental layer. Inside a closed system, there is no wind-driven soil erosion, and pest pressure is dramatically lower, meaning little to no need for pesticides. Water consumption can be reduced by as much as 90% compared to open field farming, because the water here doesn't evaporate and disappear. It circulates through the system again and again. Irrigating an open field is, in many ways, like giving most of your water away to the sun and the wind. Here, that gift is no longer made. And because the desert surface itself remains largely untouched, the fragile desert ecosystem stays intact. Agriculture expands without pushing nature aside. The human and design layer. And this is where the idea takes an unexpected turn. The underground structure stops being just a greenhouse and begins to function as a multi-purpose backbone. Imagine a sandstorm sweeping across the region. The sky turns orange. Visibility drops to just a few meters. Everything on the surface comes to a halt. But 10 meters below, nothing changes. The same stable temperature, the same silence, the same steady rhythm. That same network of tunnels could also serve as water storage, provide shelter during extreme weather events, or even connect to future underground transportation systems. A single excavation is no longer limited to a single purpose. Once you go beneath the surface, that space can continue taking on new roles. At this point, it's only fair to be honest. Not everything has been settled yet. Researchers still disagree about the long-term nutritional value of crops grown entirely under artificial lighting. Some studies find no meaningful difference. Others report subtle variations. This isn't an obstacle that stops the project, but it is a genuine question that remains under investigation, and perhaps acknowledging that is more honest than pretending we already have every answer. So what does all of this really mean for you? Perhaps it's this. Much of the land we call unusable isn't unusable at all. We've simply been looking at it from the wrong angle. Think 10, 20 years into the future. Someone living in a region affected by water scarcity picks up a bundle of fresh greens at the supermarket and glances at the label. Instead of the name of a distant port thousands of kilometers away, it bears the name of their own city. Grown beneath the quiet, flat stretch of land they pass every single day. This isn't a guaranteed future, but it is a reasonable possibility. Modular underground greenhouses may not emerge as a handful of enormous farming complexes, but as networks of smaller facilities. Independent units, each powered by its own solar panels, each recycling its own water, each operating on its own, at the edge of a town, beside a highway, perhaps just beyond a neighborhood. Drought may no longer define the limits of agriculture. Instead, it could become simply another design parameter to account for, much like earthquake resistance is in modern buildings. A school could become part of that future too. Children might watch tomatoes growing directly beneath their classrooms, learning where food comes from, not through textbooks, but with their own eyes. A city could keep its local markets supplied even in the middle of a drought. Dry seasons would no longer have to mean empty supermarket shelves. And perhaps one day, someone descending into one of these underground chambers won't remember the 48-degree heat above their head. They'll remember the 22 degrees below as the normal part. The desert's heat will no longer be the remarkable thing. The cool earth beneath it will simply be a fact of everyday life. Behind everything we've explored lies a much bigger question. Perhaps the real question isn't, can we build a greenhouse beneath the desert? In the end, that's only an engineering detail. The real question is this: how many solutions already exist in our world, hidden in plain sight, simply because they remain trapped beneath the shadow of the wrong word? The word greenhouse kept our eyes fixed on the surface. The word underground kept our minds away from agriculture. Two words, locked inside two separate boxes. And until those boxes were brought together, the solution stood right in front of us, invisible. Maybe other words are hiding other solutions in exactly the same way. Maybe something we call waste is actually a resource, placed in the wrong box. Maybe a place we describe as barren is, in fact, one of the most valuable places on Earth. We've simply never looked at it that way. Maybe the word impossible sometimes means nothing more than that we haven't asked the right question yet. The light at the bottom of that shaft was there all along. No one had simply thought to look. To be honest, we spent quite some time thinking about that question ourselves. What other places we call impossible might become possible with nothing more than a change in perspective? The endless ice of the polar regions, the dark ocean floor that almost no one ever sees, or the abandoned mining towns that were once full of life. We explored each of them, and with every one, we had the feeling that there might be a solution hiding beneath nothing more than the wrong word. But we couldn't find our own answer. Can you? Now let's return to that very first thermometer, the one sinking into the crimson sand, reading 48 degrees. Just 10 meters below, at that exact same moment, an entirely different number was waiting. The same day, the same place, two completely different worlds. Sometimes the solution doesn't require a new invention. It simply requires looking down. There are projects we haven't told you about yet. Even the engineers working on them call them crazy. We'll reveal them in the next video. Turn on notifications and be among the first to see what's coming. Real problems, realistic solutions. AG Projects.